Okay, I think I'm recording, hopefully. All right, here we go. So on ones like the first two examples that we did, um, we know what the limiting reactant is because they're only giving us one thing, right? In the third example, how much heat is transferred when 147 grams of NO2 gas is dissolved in 100 grams of water? We don't know the limiting reactant. So if you remember back, like the limiting reactant determines how much product is made, it determines how much of the other reactants are used, all that stuff. Well, because the reaction stops when the limiting reactant is used up, that also means that the limiting reactant will determine how much energy is gained or lost by the reaction. Because when the reaction stops, then there's no more energy being gained or lost. Okay? So the difference between the first two that we did here and this third one is simply that we have to figure out which is the limiting reactant first before we can find the amount of energy. Okay, so all we're gonna do is we don't have to do a whole we're not doing a whole BCA chart. We're just finding the limiting reactant. Okay. Anybody remember what we do to find the limiting reactant first? Yeah, good. Okay, so that's both steps. So first thing we're going to do is turn grams to moles for these. So we're going to go just like we would to find the energy as well. So 147 grams of the NO2. Okay, we're going to turn that into moles. So grams to moles, just like all of our gram to mole conversions. Um, so NO, where's my calculator? So N is 14 times 1 plus oxygen is 2 times 16, 46. Okay. So we're turning that into moles. So 147 divided by 46 gives us three significant figures would be 3.195. So it'd be, yeah, 3.20 moles of NO2. Okay. And we're going to do the same thing with the water. 100 point grams of, grams of H2O. And we go so it's 18 grams of water for 1 mole. And that comes out to be three significant figures again, so 5.56 moles of water. Okay, and then, like we said, the next, okay, so these are the moles. Now it's in moles of each. Now to find the limiting reactant, we divide by the coefficient. So in front of NO2, there's a 3. In front of H2O, there's nothing, so it's a 1. So we get whatever that is, 1.07. And then this is still 5.56. Okay, so what's our limiting reactant? Okay, so limiting reactant is the NO2, right? Okay, it didn't ask what limiting reactant is, but we need that to know that to do the next part of it. Okay, so once we know the limiting reactant, that's the one that we're going to turn into energy to find out how much energy, right? Now, if I piece of scratch paper here. Okay. So if I look up here, when we had moles of something and we wanted to turn it to find the energy, we went from moles to kilojoules of that, right? Okay, so if I said I have 3.20 moles of NO, oh, sorry. If I said I have 3.20 moles of NO2, and I wanted to turn that into kilojoules. Okay, you don't need to write this down. I'm just showing you something. That's why I'm doing it on scratch paper. What would I do here? Moles to, well, not to moles. I want to go to moles to kilojoules, right? Yep, like this. And then in front of the moles, where do I get that number? Yep, so that would be 3. And in front of the kilojoules would be the delta H, right? So it'd be like this. And then I'd do the math in however many kilojoules, right? Yeah, okay. So if we look at what we have here, we had the moles of NO2, and then we divided by what? Which was the coefficient. So if we look at this, we have already done this step, this part of the step. We've already divided by the coefficient, right? So the only thing we need to do to this is multiply by the delta H. So all we have to do once we find the limiting reactant one is multiply times the delta H, which is negative 138 kilojoules. And we get negative 3 significant, wait, is that right?
That's weird.
Yeah, okay, so you guys are getting the same thing I did, right? Basically
Was it
148.
Yeah.
Yeah, okay, that's right. I don't think I have anything wrong in there. No, that's right. Okay. So negative 148 kilojoules is the answer. Oh, sorry, let me get that on the screen there.
How does that work?
It's literally that's totally random. It has nothing to do with like what the number was. That doesn't always happen or anything. Okay. So once you find which one the limiting reactant is by dividing by the coefficient, the only thing you have to do is multiply times the delta H to find the kilojoules then. Okay. And then this says this wanted an enthalpy diagram too, so we can whip that up real quick, but just to have it on the notes, I guess, at least for me. So we have time, we have enthalpy, and okay, so it's negative, so that means our reactants are higher than our products. Okay. And our delta H prime is negative 138 kilojoules. Okay, so the enthalpy diagram should look something like that. Okay. All right.